Okay, so let's get started. How are you? Yes, one of the students asked to record this session. So yeah, this session will be recorded, okay? So yeah, hope this will be okay for everyone. And yeah, so let's get started. So this is the session for the factor analysis, right? So this is the small group session for factor analysis. And yes, can you hear me okay, by the way? Yeah, so silence, so means, you hear me okay. Okay, thank you. Yeah, so this session is for the factor analysis, right? This is a small group session for the factor analysis. So what I'm going to do is I'm reviewing the factor analysis, right? The concepts and procedures, the factor analysis procedures. And then I will spend 30 minutes or so to review the concept and the procedures, and then I will show you how to run the factor analysis in our studio. So that's how I plan this session. Yeah, so I will use the whiteboard. So I am probably, I don't see your screen because I'm gonna minimize your overview. But if you have any question, please feel free to stop me. You can speak or you can use the chat box. Sounds good? Okay, so yeah, let me share the white screen with you now. All right, so so we are 20, so I think I can start. All right, so then what is factor analysis? So what is a factor analysis? Yeah, so the factor analysis is a dimension reduction. It is a dimension reduction or the data reduction technique, right? So that is the factor analysis. And let me give you an example here. So say we have this question, 30 questions in a survey, 30 questions in a survey. And so you collected the data in your survey and you create this nice CSV file that contains the responses from your participants. So this is the respondents 1, respondents 2, and all the way to the respondents 100. So say we have with the sample size the 100, right? And this is the data file that you created. So this is the data file that you created after collecting some responses in your survey. And then so there are responses here, and then you can plug in this data, this raw data directly in your regression model. So then the regression equation should be y equal alpha plus beta 1 q1, because we are using the raw data here, right, to run the model, and beta 2 q2, and all the way to the beta 30 q30, and there might be other x variable as well, right here. And then there is an error term here. So this is how the regression model looks like if you plug in this data in your model directly. Then we learned this, the multicollinearity issue, right? So what if those two variables have collinear? So there's a high correlation between those two variables. So So what if this multicollinearity issue occurs from your model, right? So when those two variables are collinear, those are highly correlated, then we have this problem, right? Multicollinearity. And we don't like to see multicollinearity in the model, right? So if the multicollinearity occurs, that will produce biased estimator, biased betas, right? So we don't like that, right? And one way to resolve this issue is the factor analysis. So we can run the factor analysis to resolve this collinear issue. So factor analysis. So after you conduct the factor analysis, you will get smaller set of factors, right? Less than 30 at least, because you have the 30 questions up there, 30 items up there. So you should have less than 30 questions at least. And say we have 5 factors, F1, F2, F3, F4, and F5. And the row should be the same. So R1, respondents 1, 2, 3, all the way to the respondents 100, because our sample size is 100, right? Yeah, so this is the data that we can get from the factor analysis, model. And this is called the factor score. And what the factor score is, I will cover this later again. But factor score generally means that shows that the relationship between the respondent and the factor, right? So the correlation between the respondents and the factors. So that's what the factor scores are. So now if you plug in this data, the factors as axis in the regression model, so you run another regression model here. And then the regression model, the equation looks like this. Y equal alpha, which is the intercept, plus beta 1, F1 this time, because our X variables is now F1, F2, F3, or etc., right? And beta 2, F2, all the way to the beta 5, F5. You might have another axis here and the error term. So our new model looks like this if you plug in the result from the factor analysis here in this regression model. So now your axis here are F factors instead of the items from up here, right? So the reason why we are doing this is that we don't want to have the multicollinearity issues in the model, right? So yes, the factor analysis is one way to reduce that problem, and this is why I call the factor analysis is a dimension reduction technique. So we initially have the 30 items, but here we are having the 5 factors, right? So we reduce the dimension. So this is the factor analysis, and this is why we are using the factor analysis. So then let me move to the factor analysis model. So you have this equation in your slide. So factor analysis model. Yeah, so the equation you have in the slide looks like this. Xi is the item I, or question I in the survey context. So Xi equals AI1 F1 plus AI2 F2. And say we have the M factors, then AIM FM plus VIUI. So here this AI1 works like a regression coefficient, the beta coefficient in the regression model. So in this context, in this factor analysis context, this is called correlation coefficient of variable I on common factor I. And this is also known as factor loading values. So please recall that we retrieve this, we have this table in the slide, right? Factor loading matrix. And we saw the factor loading values in the table. So this AI1 is also known as factor loading. And this F1, F2, this is known as common factor. And this term works like error term in the regression model. So the UI is correlation coefficient of variable I. So variable I is item I, right? Item I, this one. So variable I on unique. So this is the unique factor now. So this is the unique factor, and this one is called unique factor. So this works like the error term in regression model. So the variance that is not explained in the model goes to this term. Okay, so this is how the factor analysis model looks like. And more importantly, you already know this. So we have this item set xi through xn, right? So say this is our item set. And say this is our factor set to F1 and Fm, right? So this is our factor set. And then M should be less than n, right? So M is the number of factors and n is the number of items. So number of factors should be less than number of items, right? That is the whole point of doing this factor analysis, right? So M should be less than n. So that is important point here. So if I visually, if I draw, draw some visuals that show this the equation, then say this is the total variance. So total variance of xi, and say this is the common variance.
Professor?
This is the common variance. And this is the unique variance, right? So this is the unique variance. So the total variance equals common variance plus unique variance, right? And the common variance is known as commonality. So you learned this one from the video, right? Commonality. And the uniqueness equals 1 minus commonality, right? So yeah, if we visually draw the model, this is how that looks like. So do anyone have any question?
I had a question. For n, you said that those were items, like number of items. What do you mean by that?
So a number of item, you're asking the number of item, right? So in a survey context, the number of items is the number of questions. So do you record the example in the slide? So we have their product quality, e-commerce, or things like that, right? So that is the item. So in a survey context, the item is question. And item, question, and variable, those are all, indicates the same thing.
Okay.
All right. Does it make sense?
Yeah.
Okay. Yeah. So this is the factor analysis model. So you already so learned this from the video. So this is just review, and I will go through the factor analysis steps. So the procedures, how to conduct the factor analysis, and I will cover some concepts or metrics here. So yeah, the first we do initial extraction. So initial extraction. So here in this is like an exploratory phase. So we don't know the exact number of factors yet. So we are exploring here. So mostly we want to look at the eigenvalue. And we also want to check the correlation among the variable. So if there's no correlation among the variables, among the items, there's no point of conducting the factor analysis, right? Because we cannot collapse the variable into factors without correlations among the variable, right? So that is so we check the correlation among the variable, And yeah, we can conduct this initial run with or without rotation. Yeah, so we are exploring the data in this step. So I believe you saw this factor loading matrix from the slide. So this is the factor loading matrix. So F1, say we have 6 factors here from F1 through F6. Yeah, this is the same example. So we have the product quality, e-commerce. Yeah, I believe we have 11 items, 11 questions here. So yeah, this is how the factor loading matrix looks like. Yeah, so there's a value here. So factor loading values here. So A, B. Yeah, I will, this is the actual number, but I will just write, letters here, and E, F, and things like that. So say this is the factor loading matrix, and how to compute the eigenvalue for example, the factor 1. Yeah, I believe you already know this, but I will just quickly review that. So A square plus B square and all the way to the K square, right? This is how we get the eigenvalue, right? So eigenvalue tells how important the factor is. So the bigger eigenvalue means the more important factor. Yeah, so this is the eigenvalue. So in this initial extraction stage, we quickly check the eigenvalue, right? And another thing is, yeah, this is 1, I believe, and this is 2. So yes, I didn't mention in the slide. So how to check the correlation among the yeah, this is not correlation. This is the variable among the variable. Yeah, so you can create the correlation matrix, right? Using the amount of the variables, but I will introduce this test, Bartlett's test of sphericity. So this tests the correlations among the variable. So here, the null hypothesis is no correlation among variable. So no correlations. And the alternative hypothesis for this one is at least one set of variable is correlated. So we are testing this null and alternative hypothesis here using this Bartlett's test. So the decision rule is the small p-value. So with the small, we already know this, right? So with the small p-value, we reject the null hypothesis and accept alternative hypothesis, right? Yeah, so say we have a small p-value, so we rejected the null hypothesis. That means that at least one set of variables is correlated, right? So that means, yeah, so the factor analysis is useful for this data. Yeah, so I will show you how to conduct this test in our studio later, but this is the null and alternative hypothesis for this Bartlett test. Yeah, so we just covered that the first step, then the next step would be determine the number of factors. So determine the number of factors to retain. So I introduced the several different methods, several different rule of thumbs to do that. And one of them is the script plot. And this is also known as elbow plot. So yeah, this is a script plot, and yeah, I will just draw that. And the y-axis is the eigenvalue, and x is the number of factors. And typically the script plot looks like this. So somewhere the slope is leveling off, it's stable. So we have the first factor 1, 2, 3, 4, 5, 6 over here, and roughly, so we are looking at the point where the slope is leveling off, right? So yeah, so then here, yeah, roughly maybe 1, 2, 3, 4, or 5, or 6, somewhere here, right? Somewhere here. Yeah, that's gonna be the number. That's gonna be the number for the factor, the number of factors. But you can indicate that the eigenvalue equals 1 in the plot. So say this is the eigenvalue equal 1, right? And we learned this Kaiser rule saying that if the eigenvalue is greater than 1, and that is a good cutoff for the number of factors, right? Then here, 1, 2, 3, 4, right? Up to 4, the 4 factors is greater than eigenvalue equals 1, but from factor 5, it's less than 1, right? So yeah, just based on those, this discrete plot, yeah, I may go with probably the factor 4, right? Factor 4. Yeah, so yeah, this is a one rule. And Kaiser rule, I just talked about the Kaiser rule. So if the eigenvalue is greater than 1, that is a good cutoff for the number of factors. And another thing that I introduced in the video is the cumulative variance. So if the cumulative variance is greater than 50%, and this is going to be the good cutoff. So I will draw the table in the slide. So we have 1, 2, 3, 4, 5, 6 factor. And this is the one of the output from R. So you will see that shortly in the R video. And this table is also in the slide as well. So the row here, this is the eigenvalue in our output. This is called the SS loading. And this is the proportion, variance, and this is the cumulative variance. Yeah, so you already know how to get this, the proportion variance and cumulative variance, but I will review this quickly. So yeah, so we have this number 2.714 for the first eigenvalue, and the second one is 1.984, and the third one is 1.718, and 4 is 1.376. And how to get the proportion, the variances. So this is the EV eigenvalue divided by number of factors. So we have the 11 items here. I'm sorry, this is not the number of factors. This is the number of the items. Sorry, this is the number of items. It's a number of questions, right? So eigenvalue for this factor 1 is 2.714 and divided by number of items, which is 11 in the example, right? That's how we get this proportion variance. So if you calculate that, you will get 0.247. And if you do this for the other factors, this is 0.181, and this is 0.156, and this is 0.125. So this is the same example we have in the slide. So yeah, there will be the values here as well. And the cumulative variance is, so for this one, this is the 0.247. If you add this number and this number, and that's going to be the cumulative variance for the factor 2, which is 0.428. And if you add this number and this number, then you will get 0.584. So this is the cumulative variance up to factor 3. So if you look at this here, then based on this rule, the cumulative variance rule, this is already explained the 50% of the variance, right? So yeah, so factors, the factor 4, if you added those two numbers, you will get, more than maybe 0.7 or something like that. So that's already over 50% of the variance. So if it's over 50% variance, that's going to be the good cutoff for the number of factors. So based on all this, yeah, I'd go with the factor 4, this one, right? That's what the Kaiser rule tells, and that's what the script plot tells, and that's what the cumulative variance tells. So based on all this, I will probably go with the 4 factors. And one more thing that you need to consider is interpretability when you decide the number of factors. So yeah, so the first interpretability. So the first thing that you have to consider is the common conceptual meaning. Yeah, this means that the variables in one factor share the common concept, right? So the one factor should, tell, just the variables in one factor should share the common concept. And so I will give you this example. So say we have these variables, shy, withdrawn, and distance. And this will be one factor, which is introverted. So the common conceptual meaning is that, so the shy, withdrawn, and distance share some common concept, right? So that's one thing that we consider. And another thing is the measure different construct. So the F1, so say we have 3 factors, F1, F2, F3, then those 3 factors should, measure different construct. So that's the second one. And the third one is rotated factor. Rotated factor pattern has a simple structure. So yeah, we learned that why we rotate the factor analysis, the model, right? The reason why we are doing that is purely for the interpretation. So interpretation is easier. So another interpretability that we consider is the rotated factor pattern has simple structure. Yeah, so this is the first one that we have to consider. Interpretability is the, another consideration that we have to think when you decide the number of factors. And after deciding the number of factors, now we know the number of factors, right? So we are running the final model and we are rotating. So rotation, then interpretation is easier. It's easier. And the first step is interpret solution. So interpret the solution. So yeah, so we have the factor loading matrix, which is the most important output from the factor analysis, right? And using the factor loading matrix, we are interpreting the factor, right? So for example, we name the factors, right? We name main factors. And we also figure that which items belong to which factors, right? So example from the slide is we have this factor names, functionality, images, or etc., right? So this is the factor names that we have in the slide. So in this stage, you name the factors. And the next step is calculate factor score. Yeah, I didn't deal with this factor score with the details in the video. Yeah, so you can stop your analysis here you don't need to do that. You don't need to get the factor scores unless you want to do the further analysis. So the reason why we are getting this factor score is that if you want to conduct the further analysis, such as regression analysis or cluster analysis, then you need to get these factor scores. So what the factor score tells, I briefly talked about this in the previous slide. And the factor score tells that how a given variable, how a given observation in the survey context, the observation is a person, so the respondents. So how a given observation relates to each of the factors. So this is what the factor score is. So the factor score shows that how a given person or given observation relates to each of the factors. So if I draw this table again, so say we have a 5-factor F1, F2 to F5, and the rows, we have the respondents 1, 2, all the way to the respondents 100, right? So our sample size was 100 in the previous slide. So we have certain values here, and this is the factor score, right? So this is the factor score. And this value tells that how this respondents relates to the factor. So this is the factor score, and this is the one of the output we can get from the factor analysis. And I will show you, shortly. So let me contrast this, the factor scores with the factor loading, right? So factor loading is the value that we can get from the factor loading matrix. So factor loading. So factor loading tells how a given variable, so variable equals item equals questions in the survey context, right? So how a given variable relates to each of the factor. So you see the difference, right? So the factor score tells that how a given person, given respondents relate to the factors, but the factor loading tells that how a given variables relate to each of the factors. So if I draw that the factor loading matrix quickly again, then the column should be F1 through F5. And the row is variable 1, variable 2, or things like that. And this is, again, the variable equals item equals questions. And from our example in the slide, this was product quality and e-commerce. So you see the difference with the factor scores and the factor loadings, right? Yeah, so if you want to conduct the further analysis, such as regression model, regression analysis, or the cluster analysis, then you should retrieve these factor scores from the model. Yeah, so the last step will be the result in table, and prepare report. So prepare paper. Yeah, so this is the last step of the factor analysis. And let me tell you one piece of information. I will talk about this with the details in the video. Again, the factor scores for further analysis. So we need a factor score as axis, as x variables. So as input in regression model, for example, or the cluster analysis. We didn't run the cluster analysis you will learn this in other classes if you will be taking other like data analysis or the statistics courses. But yeah, so if the factor score will be used as X variables in further analysis like regression models or the cluster analysis. Yeah, so this is all I have for the review. So yeah, so let's take a look at how we run the factor analysis model in our studio. But before doing that, do you have any questions?
Yes, Professor, I have a question. And
Sure.
in the previous example, you have the factor from factor 1 to factor 4, both, all of them, the eigenvalue is over 1. But from factor 1 to factor 3, the cumulative variance has already attained a 0.5. So should we retain 4 factors or 3 factors?
So yeah, so there should be some the subjective aspect in the factor analysis, right? I decided to use 4 factors because that's what the Kaiser rule tells, right? So yeah, so the factor 3, the reason why I didn't use the factor 3 is that let me think. So I don't have the slide here, but yes, the cumulative variance rule says that the 50% is the cutoff, but 50% plus. So it should be cumulative variance should be at least more than 50%. So 50%, 60%, 70%, that should be okay.
Okay, thank you.
Okay, yeah. Any other question? Yeah, then let me move to RStudio. So I need to use different device to run the RStudio. So I will stop this whiteboard, but this note is already on Canvas, so you can, get the documentation. But I will stop sharing this whiteboard. Yeah, I'm using 2 devices, so I need to just reset some setting here. Just give me 1 second. Okay, so can you see the RStudio here? Okay, so yes, silence means you can see that. So yeah, let's go through the steps, right? So factor analysis steps. So if you downloaded the data, you can run the model with me, but even if you cannot do that, that's fine, right? I already uploaded the syntax, so you can do that yourself later. And yeah, so this is the factor analysis, procedures, and those are the libraries, the packages that you need to load to run this factor analysis session. But the main package for the factor analysis itself is this library, the psych, right? So we are using this library for our factor analysis. And yeah, first to read the file. So this data is already on the Canvas as well. So the data factor here revised. So I'll be using this, the data for the analysis. And I will read this data file here. Then the data, the here is in the environment. So let's take a look at the data quickly. So this, the first column is the ID. So this is not part of the actual data. This is the index. So this tells that just the first observation, second observation, third observation, etc. So this is the index column. And all the other variables are the data, but the last one, satisfaction, is a y variable. So this is the dependent variable. So this will not be the part of the data for the factor analysis. But when we run the regression model, we will be using this satisfaction as a dependent variable. Yeah, so this is how the data looks like. And the second chunk of this syntax, what this does is that, yeah, so if you look at the data, the variable name is somehow, not interpretable. This is, somehow hard to understand. What is the, lead, res, or things like that. So I just want to rename the variable. So I create this vector that contain the new variable names, and this vector is variables. So I run this code, and the variable here is created, and I will apply this later to rename the variables. And so before running any model, we just want to check, the several different things. So we want to look at the data. So what is the dimension? So if I run this DIM, it shows that the number of observation is 100 and the 13 variables. And yeah, so somehow, so this, for me, I need to use these functions a lot. So I need to check the names a lot because so we have the typo errors in R a lot. So this is the function that I'm using. I frequently use, so I just copy the name and the paste in the model, for example, in the regression model. Then that reduce the typo errors. So I like this function, but this function shows that, the variable names. And the structure str, this function. So this will show you the data types, for example. So this is the integer, this is the numerical variable, or things like that. And this is the data frame. So this is, with this, we can check the structure of the data. And the summary function here, this will show you the brief descriptive statistics. So this shows you that the minimum, the first quantile, median, mean, the maximum values. So with this function, we can check the descriptive statistics. Yeah, so quickly check the data before running model. And as I said, the first variable here, ID, is the index variable. So this is not part of the data. So I want to delete the first column. So this is the, this is the syntax to do that. And the new data is here 1. So if I run this code, and here 1 is created, and you see that the ID column is gone, right? So this is how we remove the first column. And then we created this vector that contains the new variable names, right? That the vector name was the variables. And this function, using this function, we can rename the variables. So core names, and inside the parentheses, put the data name. And if I run this code and go back to the data set, now we can see that the variables are renamed. Yeah, so rename the variable and then attach the data. And here I want to check the missing values in data, because with missing values in R, this might be just R, but with missing values, we will get an error when we create the correlation matrix, right? We need to use like the remove NA function or things like that, but just before doing anything, we can just check the missing value if there's any missing values in the data. So run this code, it says there's no the missing value, right? So then we don't need to do anything. So just quickly check the missing values. And yeah, those syntax is descriptive statistics. So I told you that before running any model, it's a good habit to, look at the data using some sort of descriptive statistics. So this is also called the model-free evidences. So we want to look at the data without any models. So for example, we want to take a look at the scatter plots to see the relationship between two variables, right? And we can take a look at the distributions. We can create the histogram or density plots to see the distribution. And we can create the box plot as well. And you can create the two-way crosstabs to summarize the categorical variables, right? So we can do some sort of this descriptive statistics before running any model. And this is the syntax to create the histogram, for example, for the customer satisfaction, which is the dependent variable in our data set. Yeah, I'm not gonna go through this descriptive statistics syntax here, but this is already on Canvas, so you can use this sentence, the syntax later. But I just run this chunk here, then that will produce this histogram of the customer satisfaction, right? Then we can see the distribution of these variables or things like that. So you have this the data, you have this visualization in your slide that I believe. So I will skip this one, but again, just doing some descriptive statistics before running any model is a really good habit when you deal with the data. Yeah, so this is the factor analysis step that I went through in the review. So the initial extraction. So in this stage, so we just quickly run the model to, check the eigenvalues or how the data looks like and what the result looks like or things like that. And in this stage, we don't know the exact number of factors yet, right? So yes, in this case, I'm using the 6 factors because the number of items here in this data, except for customer satisfaction, the number of items is 11, right? And the number of factors should be less than the number of items. So yeah, I tried the 6, but you can try 5 or 6 or 7, but the number of factors should be less than the number of our items, right? That is the whole point of doing this factor analysis, dimension reduction, right? So if I run this code, so I will just quickly tell you that the syntax. So this factor, this will produce the factor loading matrix. So yeah, so this function is for the factor analysis, and this is the function within this library psych. But I already loaded this psych up there, so I don't need to load this psych library again. So this is the function to run the factor analysis. And yeah, I excluded the last variable, which is the customer satisfaction. As I said, this is the dependent variable later. So this will not be the part of the factor analysis. So I will exclude that variable. And yeah, just I give it a try, the 6 factors, and I'm not using rotations yet. So if I run this code, yeah, it shows that the factor loading matrix, right, which is the most important output from the factor analysis, and the uniqueness, right? You already learned, what the uniqueness is. So yeah, and this is the eigenvalue, right? The SS loadings, this is the eigenvalue. So in this stage, we focus on the eigenvalue, this table. So if we look at this table, yeah, so up to factors 3, the eigenvalue is greater than 1, but from factor 4, the eigenvalue is less than 1, right? So yeah, we can just get this sense that, yeah, maybe I will go with the 3 factors based on the result. And the cumulative variance here is already over 50% here in factor 3. So this also looks good as well. And we are still in the initial extraction stage. So, but this time I will run the model with the very max rotation. And the same, and the other syntax remain the same. So if I run this code, yeah, so let's take a look at the eigenvalue here. Now the eigenvalue is over 1 in factor 4, right? So this is the different result. And the cumulative variance is 50 over 50%. This is good. So yeah, factor 3 or factor 4 might be good, right? So this is yeah, this is some sort of the we can, you know, we can just get this sense. So maybe we go with the factor 3 or factor 4 here. And I talked about this Bartlett test, right, in review, right? This with this test, we can check the correlations among the variables, right? Correlation among the variable. And again, the null hypothesis is no correlation among the variable, right? And the function to do that is this. So, and we feed this correlation matrix, right? We created this correlation matrix up there, right? So this is the correlation matrix, and this is the number of observation, 100. So if I run this code, and I don't think I run the correlation matrix up there, right? So I think I missed this chunk, right? So a COR is for the correlation matrix. So this produced the correlations. So, and the correlation matrix is named this. So I will use this correlation matrix for this test. So run this code again. And this test that if you look at the p-value, this is really small, right? This is you know, there's like 96.0 before 179. So this is really tiny. So this is a small p-value. And we learned that small p-value, with the small p-value, we reject the null hypothesis, right? So the null hypothesis is here that the variables are uncorrelated, right? So with the small value, we can say that we accept the alternative hypothesis, meaning that at least one set of variables is correlated, right? And that means this data is suitable for the factor analysis. So that is the, you know, that is the thing that we can learn from this test. So yeah, we are running the factor analysis then. And the second step in the factor analysis is determine the number of factors, right? So the one way to do that is using script plot. So this is the syntax. So we first have to create the eigenvalues, right? So we are using eigenvalue to create the script plot. So this is the function EIGEN. So this is the function to produce the eigenvalue. So, and we are using the correlation matrix to get the eigenvalue. So if I run this code, yeah, this will produce the A. And yeah, so the value here, this is the eigenvalue. So we, you know, we need the values only for the eigenvalues. So I just retrieve the values from A and save it as EV, which is eigenvalue. Then we are using eigenvalue to create this plot. So if I run this 3 lines of code, then that will produce this the script plot, right? And let's take a look at the script plot again. So yeah, so we are looking at the point where the slope is leveling off, right? So yeah, so for example, yeah, this one, so this is the 4 factor and the 5, 6, right? So we are looking at around here, but looks like the 4 is the best, right? Because this is based on the Kaiser rule, the eigenvalue of the factor 4 is greater than 1, right? So based on this script plot and the eigenvalue up there, here, and I will, you know, go with the factor 4. So that is my decision for the number of factors. So now we decided the number of factors. So this will be our final model. So the number of a factor is 4, and we are using the very max rotation here. So yeah, so the same code, so we use this function to run the factor model, and we exclude the dependent variable, and we are using 4 factors and very max rotation. So if I run this code, yeah, so this is the final model, right? This is the final model. So now we want to focus on this factor loading matrix, right? So we want to name the factors, and we want to figure that which items belong to which factors. And if you look at this eigenvalue, this looks good as well, because the eigenvalue for the factor 4 is greater than 1, and the cumulative variance is over 50%. So yeah, so this looks good. So based on this final model, then we name the main factors. So from the example in the slide, we have these names for our model. So this is the functions, names, techniques, and warranty product lines. So you name the main factors based on the result, based on the factor loading matrix mainly. Yeah, so you can stop here for the factor analysis itself. But as I said, if you want to conduct the further analysis, like regression models or things like that, using the factor scores from the factor analysis model, then this is the syntax to get the factor scores. So everything remains the same. So syntax is the same except for this argument, the scores. So if you add the scores argument, this will produce the factor scores that I showed you in the review, right? So let me run this code. And yeah, so fit for, so if you look at here, the environment, if I click this fit for the score, this one is the factor scores. So let me click this one and click enter. And if you look at console here, this is the factor scores that I told you in the review, right? So we have here the 4 factors, and the row here is the rest. So this is the respondents, right? So this is the observation, respondent person 1, person 2, person 3, or things like that. So this is the factor score that we will be using as X variables in the further analysis. So what I'm doing here is that I save these scores under fit for. I save this as a factor score, but first I want to convert that as data frame and then save it as factor score. So if I run this code, you can see that the factor score here in this environment is created, right? So this is the same data set in the console, but this is in the data frame format. So this is the factor score. So then let's use the factor score for the regression model. So yeah, the factor score here. So we want to, so if you look at this data, there's no Y variable, right? There's no dependent variable here. So I need to combine the factor scores with the original data, which is hair, to get the Y variable, right? So I'm using the cbind to combine those 2 data sets. And then the new data set is named hair factor. So let me run this code. And then hair factor is created here. So the same data set, but the 4 factors are added to the original data, right? Yeah, so yeah, with this data set, I will run the regression model, and the Y, the dependent variable, is satisfaction. And now the factors are the X variable, right? So the 4 factors. So we have a factor 1, factor 2, factor 3, factor 4 as X variable, and the data set is hair factor. And I'm using LM for the linear regression. So if I run those code, it will show you the result. So if you look at this console, yeah, this is the resource. So now the factors are the X variable, right? So those are X variable. And you can take a look at the probability, the p-value here. So the factor 1, factor 2, and the factor 4 are related. Have significant relationship with the satisfaction. So let's go back what the factor 1 to 4s are. So yeah, so factor 1 is functions, factor 2 is images, and factor 3 is product lines. So the functions, images, and product lines are positively related with the satisfaction because here the beta coefficient are all positive, right? Yeah, so that's how we use the factor scores in the regression model. Yeah, so this is all I have for today. So do you have any questions?
I have a question.
Sure.
I see that you added the factor scores back to the original data.
Mhm.
How does R determine what to use again? I know it's now used. They're now used as X variables, but I don't understand how it knows what
Right,
to use, what not to use.
Yeah. That's a good question. So let me go back to the original data here, right? So the ID is the index variable. This is not part of the data set. We are using from product quality through this was delivery speed. Yeah, this is not understandable. So product quality through delivery speed, right? So this is the this was the data for the factor analysis, right? And we reduced the dimension from, I believe those are the 11 to the 4 factors here, right? So if you run the model using the raw data, this can be individual column can be X variable. So product quality, e-commerce, technical support, those can be the X variable, and the satisfaction is the Y variable, right? But now we are using the factors instead of the raw data because these raw variables are reduced to the 4 dimensions, 4 factors, right? So this is the original, the dependent variable satisfaction. So we want to combine the original data with the factors here, then we can see the relationship between the factors and the satisfaction, which is the dependent variable. So does it answer your question?
Well, I understand that we're using satisfaction, but I guess I was just I didn't understand how the 4 R knows to use the 4 factors instead of all the other columns. Because in my mind, I would have just added satisfaction to those 4 factors and then just run it like that.
Yeah, so if this is the factor analysis, session. So I just want to show you that how to use the factor analysis in the regression model, but you can use the raw data itself, the original data, which is the delivery speed and, the warranty claims or things like that. You can use that as it is, but if you find some kind of like, let me say that's like in a real research setting, you may want to use the raw data themselves, right? If you don't want to, use the underlying factors as X variable, that's okay, right? But what if you find some kind of the multicollinearity issues among those variables, right? What if the 2 variables are highly correlated, right? Then, yeah, the factor analysis may be one option that you can consider to remove the multicollinearity issues in the model. Does it answer your question? So you can use the original data, but but the factor analysis is one way to, remove the multicollinearity issues.
Yeah, that's what I'm worried about. I was thinking that instead of having the original data on this data set, you would just have the factors and satisfaction.
Yeah, so what is the overriding point here? The multicollinearity?
So if you, I was thinking as you went through this, if you added those 4 factors back to the original data, how would R know to make the new model from just satisfaction and the 4 factors?
Oh, that's what you have to specify in the model. So
Okay.
here you specify the factor 1, factor 2, factor 3, and factor 4, right?
Okay.
Right.
I missed it. Okay.
Oh, okay, great. That answers your question, right?
Yes.
Okay,
Thank you.
great. Okay, any other questions? Let me check the chat box. Yeah, no question here. Yeah, so the syntax and the data set and the note are all on Canvas already, so you can run the model yourself, right? So yeah, so that's all I have. So if you don't have any questions, I can, finish here now. But if you have any questions, after this session or while you were running the model, if you have any question, please feel free to contact me. Yeah, any other question? Okay, yeah.
I have a quick question. I don't know if this is a dumb question, but I was just a little confused on what a factor is exactly. Like, would you say it is like a description of many not a description, but a kind of like a many variables grouped into one? Is that kind of
Yeah,
what?
that's right. Yeah.
Yeah.
That's
Okay.
exactly right. So we found, certain set of variables that are highly correlated, right? That means, so in a survey context, that means that the items, the questions may ask something similar, right? So going
Right.
back to that example, the shy, withdrawn, and the distance. So those 3 variables from the survey, those 3, say that those 3, the responses from those 3 questions are highly correlated, right? And that means that may ask probably one underlying factors, because those 3 variables are highly correlated. And again, going back to the regression model, we don't want to have the multicollinearity issues, right? If we use the variables themselves, shy, distance, withdrawn, those are highly correlated in the model, and this is not good in the model, right? That will produce the biased estimators. So we don't want that to happen, right? So that's why we are doing this, one reason why we are doing this, the factor analysis. But you are correct. So the similar variables are collapsed in one underlying factors. So that is what factor is.
Right. So when you say variables, is it the same thing as questions, or?
Correct. Yeah.
Yeah. Okay.
Variable equals questions equals items.
Wait, say that again.
Oh, so variable equals questions equals items.
Oh, okay. Okay, thanks.
Any other questions, comment? Okay, sounds good. So I will finish this, but if you have any questions, feel free to email me. Thank you.